All right, now we're looking at section 1 of our trigonometry and special right triangles unit. Our section 1 is all about the Pythagorean theorem and its converse. And we're going to start off by reviewing some of our concepts from radicals. Remember, radicals are basically just anytime we have a square root symbol over our number. Those are called radical numbers. They're also called, or can be called, irrational numbers if they don't actually simplify. So first we're going to go over simplifying radical numbers. Now, remember, if we have a radical or square root of 112, what we're trying to do is break this down into things that or like the biggest number that we can take out that does still have a square root. Now, remember, we can always find those square roots if we make the list of all the square numbers. So like 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and so on. So we can make a list of all of these and try to find the biggest one that we can take out. Now when we do that, we'll find that the biggest number we can take out is 16. 16 is 4 squared, so it's easy to find the square root of 16. Now 16 times what would make 112? It's 16 times 7. Now this number we can find the square root of, this one we can't. So as we continue to simplify it, we would call it 4 times the square root of 7. Square root of 16 is 4. Square root of 7, we don't know. There isn't an exact number for sure. At least it's not a whole number. It would be a really long decimal number that never ends. So at the end, we can simplify this down. Instead of putting in this multiply sign, 4 times the square root of 7, we would just call it 4 square roots of 7. So it's saying 4 of these amounts, 4 times the square root of 7. So that would be the most simplified form to say the square root of 112. Now let's look at another example. In this case, we have 5 square roots of 45. So in this case, we already have a whole number being multiplied in there. So 5 stays alone, and it's just the square root of 45 part that we're breaking down. Now again, the biggest number we can take out of 45 that does have a square root would be 9. Square root of 9 is 3, so we can work on simplifying that. What times 9 is going to be 45? Well, it's 5, so it's square root of 9 times the square root of 5 would make the square root of 45, and all of that is still being multiplied by this 5 right here. Simplifying everything down, we have 5 from before times 3, because the square root of 9 is 3, times the square root of 5, because we don't know what the square root of 5 is, so it has to stay like that. Simplifying this out, 5 times 3 is 15, and we don't need a multiply sign anymore. We would just say 15 square roots of 5. So in the end, this would be our most simplified form of 5 square roots of 45. Now let's try this one where we have the square root of a fraction. So we have the square root of this fraction, 24 over 80. Now that square root can be applied to both pieces, the numerator and the denominator. So we call it the square root of 24 over the square root of 80. Anytime you have the square root of a fraction, you could just apply it to each piece individually. As we simplify that down, we have to break down square root of 24 and the square root of 80. So it would look like this. 24 is going to be 4 times 6, and we can get the square root of 4. We know what that is. 6 we can't. 80 is going to be square root of 16 times 5. We know square root of 16. We don't know the square root of 5. But both are going to be under the square roots, so it would multiply to the square root of 80. As we simplify that down, square root of 4 is 2, square root of 16 is 4. So it's 2 times the square root of 6 over 4 times the square root of 5. Now, as we're simplifying this, 2 over 4 is the same as 1 over 2. Because multiplying and dividing, this sign is a multiply, so is this one. This bar means dividing. By our order of operations, multiply and divide happen at the same time, so we can do them kind of in whatever order we want. We can divide the 2 divided by 4 right away and simplify that to 1 over 2. So now that we simplified it 1 over 2, it's going to look something like this. 1 times the square root of 6 over 2 times the square root of 5, which we can just simplify as the square root of 6 over 2 square roots of 5. Now in the end, you always want to rationalize the denominator, but we won't do that on this example. I just want you to kind of circle it and make note that we still need to rationalize this denominator, and that'll be an example on a different list. Let's look at this one. We have the square root of 24 over 2 square roots of 3. Now square root of 24 we can break down into square root of 8 times 3, or square root of 3, I should say, because 8 times 3 is 24. We'll leave them both underneath a square root symbol. So what this means, this 2 times the square root of 3, is, remember, it's like saying, I want to move this over a little bit, 2 times the square root of 3. Since we have the square root of 3 in both cases, we can essentially just cancel those out. It's like a 4 over 4 just means 1 over 1, or anything over itself just kind of cancels out. So we'll get rid of that, and now our fraction looks like this, square root of 8 over 2. So let's simplify that some more. 8 is 4 times 2. So the square root of 8 is the square root of 4 times the square root of 2. Now why did I break them up into those ones? Because we know the square root of 4. So it becomes 2 times the square root of 2. And what can we cancel out of those? The 2 and the 2 will cancel out. So the only thing left in the end is just the square root of 2. So our most simplified form of saying square root of 24 over 2 square roots of 3, we can simplify it down to just simply square root of 2. Now this last one, e, because we have the square root of 5 on the outside of this parentheses, and the inside there is square root of 15 plus 3, this means that we're multiplying. So we have to distribute this square root of 5 to each of these pieces. Square root of 5 times the square root of 15, square root of 5 times this whole number, 3. What that's going to look like is, well, 5 times 15 is 75. So square root of 5 times square root of 15 is the square root of 75. Square root of 5 times 3 is 3 square roots of 5. Now, this one we can't break down anymore. Square root of 75, though, we can break down into square root of 25 times the square root of 3. Because 25 times 3 is 75. Now, simplifying that some more, square root of 25 is simply 5. So we have 5 times the square root of 3 plus 3 square roots of 5. Simplify it all the way, it's 5 square roots of 3 plus 3 square roots of 5. Now, can we combine these two? No, we can't, because the square root of 3 is very different from the square root of 5. This one is going to be less than 2. It's going to be like 1.2 something. This is going to be a little bit more than 2. How do I know that this is less than 2 and more than 2? Well, because these are on different sides of the square root of 4. Square root of 4 is exactly 2. This is going to be smaller than that. This is going to be bigger than that. So these are not the same number, so we can't just add them together. Even though they both have a 5 and a 3, this has a whole number 5, this has a whole number 3, this has a radical number 3 and a radical number 5, so these cannot combine. It is simply, in the end, our most simplified form, 5 square roots of 3 plus 3 square roots of 5. And that would be how to simplify e. Now let's look at some operations. If we are just adding square root of 5 plus 4 square roots of 5. Now notice on this one, there's just 1 square root of 5 here. So if we have 1 square root of 5 plus 4 square roots of 5, since these do match, square root of 5 and square root of 5, we're asking ourselves, really, how many square roots of 5 are there? There would be 5 square roots of 5. So this would be the most simplified way to say square root of 5 plus 4 square roots of 5. Now if we have 2 square roots of 3 minus the square root of 5, again, these don't match. It would be like saying 2x minus y. This is x terms, this is y terms. We can't take y terms away from x terms. Or at least when we're simplifying, we can't combine them as though they were like terms. So this would be the most simplified form. You would just leave it as 2 square roots of 3 minus the square root of 5. How about this one here? We've got 5 square roots of 7 plus the square root of 63. Well, 5 square roots of 7 has to stay. We can't break it down anymore. 7 does not have anything that multiplies to it. But square root of 63 is 9 square roots of 7. Why did I use 9 right here? Well, because that's the biggest square number that I can take out. What is the square root of 9? It's going to be 3. So we call square root of 63 3 times the square root of 7, or 3 square roots of 7. Now we have 5 square roots of 7 plus 3 square roots of 7, which essentially means we can think of it as like 5x, calling the square root of 7x. We call it 5x plus 3x. Now these are the same term, right? We have x terms and x terms, In this case, we can think of it as we have square root of 7 terms and square root of 7 terms. So when we combine them, we would just call it simply 8 square roots of 7, because 5 plus 3 is 8. So in the end, our most simplified form, 8 square roots of 7. Here we have some more operations. So we're multiplying the square root of 6 times the square root of 18. Now we can combine those together and just call it simply the square root of 108. Once we have it all as one square root, now we try to simplify it by breaking down the smallest, or should I say the biggest square numbers that we can take out so that we have the smallest numbers left possible in a square root. So 108 breaks down into 36 times 3. Now again, why do we use 36? It's because it's the biggest square number that will go into 108. Now what I mean by square number is there is a number times itself that would equal that. What number times itself is 36? It is 6. So square root of 36 times the square root of 3 becomes 6 times the square root of 3, which means in the end it's just 6 square roots of 3. So this would be our final answer here. That is the most simplified form of square root of 6 times the square root of 18. Now let's look at E. We have the square root of k cubed. Now because cubing, or to the third power, is bigger than squaring, and this is a square root, or you can always think of it as there's a 2 out here. There's a power of 2 right here. This is bigger, so we can break it down into smaller pieces. Just like this one, we combined into a bigger piece. Well, you could break this down into 6 and 18. We can break this k cubed down into k squared times just k, or k to the 1. Because k squared times k would be k cubed. Now that we have it broken down into one of them being squared and one of them just alone, we can figure out what is the square root of k squared. Well, that squaring and square root will go away, so it's just k times the square root of k, which means in the end it's k square roots of k. Now why do we want to break it down? We always just want to take out as many squares from underneath the square root as possible. You want this number underneath the square root as small as you possibly can have it. And k cubed is going to be bigger than just k. So we want to take out anything that we possibly can. But in the end, this would be our most simplified form. Now let's look at F. We have 4 square roots of 27 all over the square root of 48. And we can break down both of those on top and bottom. 4 square roots of 27, well 27 is 9 times 3. Again, I use 9 because we do know that square root. 48 is 16 times 3. So square root of 16 times square root of 3. And we know the square root of 16, so that'll help us break things down. As well, we also can see that square root of 3 will cancel out in both of these. So after we cancel it out, all we have is 4 times the square root of 9, which is actually 3. And on the bottom here, we just have 4. Now we can cancel out those 4's, which means in the end, all we have left is 3. So 4 square roots of 27 over, or divided by, the square root of 48 would just become 3. All right, for our last few examples in this video, we're going to look at rationalizing the denominator. What we mean by that is, in our denominators, we do not want to have any square roots. Now, in each of these, there are square roots. So, we do not want to have that, so we need to rationalize them. How do we rationalize the denominator? We multiply the top and the bottom, the numerator and the denominator, by the same number. Now, that number will usually be one of the square roots that we have on the bottom. So let's see how that looks for this one. If we have 1 over the square root of 2, we would be multiplying by the square root of 2 on both the top and the bottom. This is because the square root of 2 times the square root of 2 in the end would equal the square root of 4, which in the end just equals 2. Anytime you have the square root of something times that same square root, basically just gets rid of that square root. So it would just become 2. So if I had like the square root of 7 times the square root of 7, that would just equal 7. It has to be, because this would become the square root of 49, which is just simply 7. So that's what we're trying to do, is basically just get rid of the square root in the bottom. So like I said, we would multiply the top and the bottom here by the square root of 2, which means in the end we're left with 1 times the square root of 2 is square root of 2. Square root of 2 times square root of 2 is 2. So we have the square root of 2 over 2. And this would be our simplified form. Let's look at example B. We have 5 over the square root of 3. So again, we're multiplying the square root of 3 on top and bottom. Square root of 3 times the square root of 3 becomes 3 on the bottom. So we have 5 square roots of 3 over 3. And that would be our simplified answer with a rationalized denominator. Notice in the bottom, this denominator, there's no longer any square roots. It's just whole numbers, which is what we were looking for. In this example, we have this 3 times the square root of 2 all over the square root of 5. And we need to get rid of that square root of 5, so we multiply the top and the bottom by the square root of 5. On bottom, that leaves us with a 5. Oops. Wait. That leaves us with a 5. On top, that leaves us with 3 times, it's no longer the square root of 2, it's the square root of 2 times the square root of 5, so it's the square root of 10. So we'd have 3 square roots of 10 all over 5. Again, this is called rationalizing the denominator, because in the end, we want this number to be rational. It's technically irrational if you have the square root sign here. Square root of 5, we don't know that number. It's a random number with a lot of decimals in it. We don't want that. We want whole numbers or rational numbers at the bottom here. Now let's look at this example. 2 square roots of 6 over 3 square roots of 3. Now, instead of multiplying the top and the bottom by the square root of 3, we can just break it apart. And we'd find that 2 square roots of 6 is the same as 2 times the square root of 2 times the square root of 3. The square root of 2 times square root of 3 is square root of 6. When we break it apart like this, that means we can just cancel out the square root of 3 in both cases. Now, like before, there's no square root in the bottom, which means we've accomplished our goal of getting all the square roots in the denominator gone. So our answer would just simplify down to 2 square roots of 2 all over 3. So again, rationalizing the denominator, your goal is just to make sure there's no square roots in the bottom. And that'll be it for our first video. Our next video is going to go over reviewing the Pythagorean theorem.